Okay, let's start with the next session. We have a roundtable with the coordinators. So I would like to ask the coordinators, Valentina, Jimmy, Konstantinos, Jaione, and Angela. Because now there is no order, just take a seat and feel comfortable. Okay, so first of all, thank you very much for offering this this workshop. We have 1 hour. I will give you the floor for 1 minute each to present your project, because all the people have also the slide in their folder, and then we will start with questions. So let's start with the first project, which is AMBHER. So you are the lucky one.
Yes, thank you. I mean, it's only one slide.
Yeah. So.
Hello everyone. I know you are all relaxed after a nice lunch, so maybe you won't be listening to half of what we say. Anyways, I'm Angela. I'm from Technalia. I'm a project manager there, and I'm coordinating AMBHER project. About AMBHER project, we are in month 46. Just finished our month 46 consortium meeting yesterday. So we are almost completing our prototypes, and we are validating everything right now. So what is AMBHER project? It's basically, we want to develop hydrogen storage technology. And in the AMBHER project, what we do is that we have two types of hydrogen storage. One is long-term storage, and another is short-term storage. So I'll start with the short-term storage because then I will get a flow. So the short-term storage, we are using MOFs. We are developing H-1 and aluminum fumarates. So these two MOFs we are developing, and we are testing about the hydrogen storage capacities, and we are validating it, and our results will be out by May 2026. And then we have a long-term storage, which is ammonia synthesis, the whole theme of this workshop. So the ammonia synthesis, we are doing it with a catalytic membrane reactor, where we develop catalyst, and we also develop carbon membranes, and we try to validate the whole carbon membrane reactor, and we are getting much better results than an ordinary catalytic reactor. So we are validating it right now, and we are expecting really good results by the end, like in 2 months. Also, in the framework of AMBHER project, I think we already met, Buddy from JM. She is working on catalyst. And then Matunde, we're working on the LCA analysis. So we are planning to develop a full LCA, LCC, and health and safety for this project. And also we would like to promote dissemination and a lot of communication regarding ammonia, especially because we know ammonia is a taboo molecule. So we are also planning to do that in this project. And yeah, in 2 months it will be over. And I hope you will be following us then. And please feel free to contact me if you need any networking from my side. Thank you.
Thank you very much, Angela. Because you are there.
You want me to say APOLO? Oh.
No, there is Andrea. So, Jaione.
My turn. Hello, everyone. Well, I will present AndreaH project. It's a project in which we are cracking ammonia using an innovative membrane reactor for the hydrogen production. We are developing different technologies based in this membrane reactor, in which we are developing the catalyst, structured catalyst with no or low content of ruthenium. We are also developing carbon molecular SiC membranes. also novel solvents for polishing the hydrogen. And we are also carrying out LCA, LCC, health and safety analysis. We are also studying different business cases, and it's very interesting. Well, maybe we can explain later, but we have also studied one case in which hydrogen is produced in the same place where it is consumed in Germany, and another one, the AndreaH case, in which hydrogen is produced in another area and transported as ammonia to the place where it's used as hydrogen. And you can see there the scheme of the technology, where you have seen already this scheme, in which we have the membrane reactor. There will be integrated the membranes together with the structural catalyst. We will have a stream with hydrogen that still has not reached the purity we want. So we are using solvents to achieve this hydrogen purity. The project started in July 2023. Now we are in month 34. And you can see there which are the companies that are and research centers that are involved in the project. And of course, if you want to make any questions, you can ask.
Thank you very much, Jaione. Good. The next one is Apollo.
So hi again. Hello. So I'm also the coordinator of, I think it's yeah, there is some animation I was supposed to just.
Yeah.
So I'm here representing Apollo project. You might have listened to a talk already on Apollo. So what in Apollo project is the opposite of AMBHER. It's the ammonia cracking. So we are planning to decompose ammonia into a very ultra pure hydrogen, and this hydrogen will be used in an advanced fuel cell system. And then we also is planning to mix this hydrogen with ammonia to run an ammonia engine. So we have basically two prototypes here as well. As we know, the main partner for this Apollo project, apart from Technalia as a coordinator, is H2 site. So they will be the ones who will develop the catalytic membrane reactor, and these membranes are palladium membranes. And we are also developing catalysts. JM is in charge of it. And then we also, since we need a very advanced, like ultra pure hydrogen for the fuel cells, we would be also developing some hydrogen pollution and solvent, and that will be done by JM again. And then, so this hydrogen, this fuel cell grade hydrogen will be used by two fuel cell companies, from Norway, Corvus, and from Italy, Nuvera. And they would be testing this as a whole prototype, and then we would be using this for maritime applications. And the second prototype is with ammonia hydrogen blend, and same catalytic membrane reactor. But in this case, since we don't want ultra pure hydrogen, we would not be using the hydrogen polishing step. And this, so whatever comes out of the catalytic membrane reactor, we would be using it by the engine developed by LEC from Austria. And this would again be tested for, like, it's a TRL5 level project, so it won't be in the actual ship, but it would be tested for maritime applications as well. And then in this framework, we also have LCA, LCC analysis, which is done by Chalmers. And also, again, we need a better PR for ammonia. And that's where we also is contributing a lot towards the dissemination and communication. So again, any questions regarding Apollo project, please feel free to contact me. Thank you.
We have Caipirinha project. So
Hi all, I'm Kourtzanidis. I'm representing CERT. We're coordinating Caipirinha project. We talked a lot about ammonia cracking. Our project aims in the direct combustion of liquid ammonia using non-equilibrium plasmas. So our concept is focusing on developing an advanced liquid ammonia combustor, what we call the plasma mixed ammonia burner. And how we do this? We do this by starting by developing detailed plasma combustion kinetics, something that's not easy. Then using advanced multi-physics simulation, including plasma simulations, combustion, reactive, non-reactive, CFD, to understand the physics involved in the combustor. We have a company that will deliver unique liquid ammonia injection systems, which is very important also for the domesticization of the liquid ammonia fuel. And then using tailored plasma technology, we aim to achieve combustion of liquid ammonia and providing reduced emissions and enhanced efficiency. All these combined with some smart combustion control strategies in order to achieve TRL4 at the end of the project. And we'll demonstrate our capabilities of our combustor in Cardiff University, which is our demonstrator partner. Of course, we'll focus and we'll follow a holistic approach also to ensure the environmental, the social, and economic sustainability of our technology using classic LCA, LCC, and social LCA analysis, and perform some market research and uptakes strategies. What we aim in the end is to have a direct liquid ammonia combustion system with ultra low emissions, with high thermal efficiency, presenting an enhanced ignition quality, and in the end having a carbon-free combustion with reduced fuel storage needs. We are very lucky to have a very unique consortium with very strong partners, a part of us at Cardiff University. We have Cleaner Powers, NRS, Cleos, Exedesis, Lutz University, Onera, RINA, and University of Birmingham. And in the end, we aim to demonstrate the efficiency of our technology in different sectors, from power generation to maritime, aviation, and for the automotive sector. That's all. Thank you so much, and I'll be happy to answer your questions.
Thank you very much. The next one is Fausto. Jimmy.
I don't know if it is with
Fausto.
a few animations, is it?
Yes.
Yes, all right, great. Thank you very much. So good afternoon, everyone. My name is Faria. I'm from University of Twente. I'm the coordinator of the Fausto project. What we are aiming at is to create a flexible ammonia synthesis reactor system. The idea here is that you could ramp up and ramp down the catalytic conversion of nitrogen and hydrogen to make ammonia. And more recently, thanks to WIDERA, these widening European funding, we managed to get CERT also on board in this project to work on the ammonia cracking as well in a flexible platform. The idea is for that is to get to TRL4 at the end of the project. This is our actually first year of operation, so we are just starting the project. I'll tell you more about the details later on. The concept relies on creating new catalysts and new reactor components that can allow us to propagate heat very efficiently and convert nitrogen at lower temperatures, allowing us to have a lower thermal inertia in the system so that we can ramp up and down in operation much faster. So that's in a nutshell, the project. We're more than happy to listen to your questions and hopefully maybe establish new cooperations after this workshop. Thank you.
Thank you very much, Jimmy. The next one is measured. Valentina.
Thank you, Fausto. My name is Valentina. I represent TWE with the coordination of AMBHER project. AMBHER works on the membrane scale-up for chemical industries. And basically, it is about scaling up a technology. We don't really work with ammonia, but what we do is that basically we use the same technology that was presented in AMBHER, Ollo, and AndreaH, which is membranes and membrane reactors. And then we show that it's possible to use this technology for several applications. How the project works is that we have a consortium of 17 partners, and then we work in 3 lines. So we apply membranes for 3 different applications, and in particular, they are per-evaporation, membrane distillation, and gas separation. And the idea is to basically try to deliver TRL7. And then that's basically what we do. When it comes to per-evaporation, basically what we do is that we use ceramic membranes to basically do process intensification on acrylic acid production. When it comes to gas separation, we use carbon membranes for hydrogen deblending. And when it comes to membrane distillation, what we do basically is wastewater treatment. So this is basically a measure project in short. Thank you very much.
Thank you very much. So, we do first something on the computer. I will stop sharing. So if there is any question, we can see on the screen. So for the people online, please write your questions, if any, in the chat. And I will now open the roundtable for questions. Is there any question for the different projects? Yes.
So thanks everybody for the presentation of the project. I am from AMBHER project, so basically I'm focusing on developing membrane reactor for ammonia synthesis. And let's say we would like to foresee this membrane reactor where they can in future be applied if in case they're gonna work. So my curiosity is for Faria, because you say that basically the project is about developing some kind of system in which you basically have hydrogen which stops, and then yeah, you want to, let's say, develop new technologies for producing ammonia in case you don't have a continuous flow stream, right? So I was wondering which would be the first approach from the project to understand how you can have this hydrogen in, like when you have this intermittency in hydrogen, how will be the reactor? How will it look like the reactor? Because I assume you also don't have big scale up, like you cannot foresee big scale up. So how you would develop the design of the reactor in general, and therefore also the catalyst inside? Thank you.
Thank you very much for the question. Jimmy.
Going to be working a lot. That's good. That's good. Thank you for the question. So I'll try to answer to the best way I can to your question. The idea in general is to leverage absorption enhanced AMBHER. And of course, as you know, that's not the most scalable process. So we cannot go to gigawatt scale with such a system because the salts are, you will require a very large amount of salts to do the absorption of the ammonia after the reactor. So in that sense, we're thinking on, let's say, medium scale type of applications. That means decentralized ammonia synthesis, right? In that scenario, so we are thinking on a structured catalytic beds that can enhance heat transfer inside the reactor. The reaction is highly exothermic, so we're trying to remove the heat in that way as effectively as possible. And then the second aspect of the project is to try to lower as much as possible the operational temperature and therefore also the pressure of operation. And you saw that we're going to be ramping up and down maybe gas flow rates or so, but maybe that we have to increase maybe recycle or so to maintain, let's say, maybe to change the reactor from, let's say, idle to a maximum operation. And so that is maybe as much as I can tell. I can tell you more about what the ideas we have for catalyst development to go to lower temperatures in the afternoon. But in a nutshell, that is essentially what we're thinking of.
Thank you very much. Other questions? I have a question for Caipirinha, just because it's a question that all the people ask me when I speak about plasma. So when you use plasma for ammonia, you do ammonia cracking, right? Or so how is the energy that you put in compared to the energy that you get out?
So you're asking about the dissociation of ammonia with plasma. It depends a lot on the plasma system that you have, right? So there are plasma systems. In Caipirinha, we're aiming to use what we call non-second pulse discharges for dissociation of ammonia. And there, the energy is put in very, very short time. So we have a lot of very big energy input to crack the ammonia. Then, if you're talking about the whole efficiency of the combustion itself, right? Because you have to burn this. I mean, this is something that we should see for sure. We don't know that yet directly. I don't know. I cannot give you a direct answer on that. But there is a presentation afterwards from Agustin. I think that would be very interesting because he will present some of the preliminary results. Caipirinha is a very, very early stage, right? We're in the first year of the project. But he will present some preliminary results, and we see that the efficiency, the whole thermal efficiency of combustion in the end, can reach levels that they're quite competitive. I don't want to give numbers because there's no point in giving numbers now, to be honest.
We will follow the project.
Yeah, I think that's the best thing. Thanks.
Line.
Yeah, there is a question online, perhaps you can read.
What is the injection pressure?
Is that one? Yeah, is that one? But I think was before.
They might be for the
Yeah, was for Caipirinha.
I think it's, well, yeah, the question is what is the injection pressure for the ammonia system? Injection pressure is achieved. So again, what we aim to do in Caipirinha is to use liquid ammonia direct injection, right, in the combustion chamber. The combustion and the whole process we focus on is under atmospheric conditions. So we want to expand this liquid ammonia into an atmospheric pressure of the chamber. Why we do this? Because we have to focus on some kind of standard, let's say, conditions and see if we can achieve the combustion that we want, because this is a very, very challenging aspect on its own. Of course, going further upper in pressure, it's something that would be way, way more useful. But I think the first step would be to focus on atmospheric pressure.
Thank you very much. Yes, I will start from you.
Of course. Neil Neff of University of Turkey. Just following up on the same question, are you atomizing the liquid so that there is some pressure needed for the atomizing, right?
Yeah, I mean the liquid ammonia is pressurized anyhow, right?
Okay, so you use the pressure to.
Yeah, it's expanded.
Thank you very much. I will give that.
Thank you. I will have a question for the ladies after, but I just wanted to ask a question to both Jimmy and Konstantinos. So it's regarding the size. So first for Jimmy, so ammonia synthesis, and I think we have someone from ThyssenKrupp behind. The size of ammonia plant ThyssenKrupp is building is like 4,200 tons of ammonia per day. And now transitioning to renewables, this plant will be much smaller because obviously it's the amount of renewable you have in a certain place could be 100, 200, 300 megawatts of power. What is the size of the future green ammonia plants that you think will be? That would be my first question. But I have a second question for Konstantinos. Opposite way, you are developing plasma process for combustion, which are their big systems, especially for shipping engine. So what is your strategy for upscaling? Is it numbering up? How do you fit to the market?
So first, Jimmy.
Thank you very much for the question. We're thinking on the tens of megawatts type of scale for the ammonia synthesis. So these are, I mean, in the world of ammonia, these are really small scale ammonia systems. But let's say for a lot of regions in the world, the capex barrier for a world scale ammonia synthesis plant is too high. And so for those markets, these kinds of solutions will make a lot of sense.
Yeah, upscaling, great question. Once again, we are a low TRL project, right? So upscaling is a big part of what we are aiming to do to study how we're going to go to bigger scales. What we aim to do in the project, though, is a demonstration activity, is a lab scale demonstrator. It's going to be, of course, smaller scale. So a serial combustor that's going to be lab level, let's say. I think if I want to give a perspective, we want to design something that can be as modular as possible and can be upscaled by modularity, so by adding more modules. I think this would be my idea of how we can upscale this system, because indeed plasma systems are complicated on its own. Upscaling of them is complex in any kind of industry. So it might be even more hard to do that in combustors, but we can think of modularity as a solution to our science.
So, Konstantinos, I saw another question for you, but I think was for both. This one. Perhaps you can read the question.
So the question is, for maritime application, what remains the hardest bottleneck for direct ammonia combustion to become commercially viable? Okay, what is the question? Is it ignition stability? Is it NOx N2O control? Is it ammonia slip or system integration? I would say it's all of them. Honestly, you just mentioned all the challenges that we aim to tackle, at least in Caipirinha. I mean, we aim to tackle ignition stability, NOx and N2O control, ammonia slip, not system integration, because we're not really integrating this into the system. Again, it's a low TRN project, but I think that all the others are very, very important, because ignition and flame characteristics of liquid ammonia, especially flames, are very challenging to control and to enhance, let's say. Emission control, as you all know, it's extremely, extremely important, as well as ammonia slip. We think that by using non-equilibrium plasmas, we can mitigate all of them, and then system integration is the next level.
And I think the next one on the pressure is also for you.
But ammonia is available in bottle pressure, which is around 70 parts 2 degrees. This means it's a pump which can handle phase change of ammonia may be required. Yeah, so I think that this deals with the injection of liquid ammonia and phase change, of course, in the combustor. As said, we're very lucky to have a company, Cleaner Power, which has huge experience in liquid fuel injection, and they are providing very, very tailored injection systems that will try to mitigate all the systems, provide the atomization that we need, very, very fine atomization as we need, and then everything about phase changes and other very complicated, of course, multi-phase phenomena that happens when we inject in ammonia in an atmospheric pressure combustor is things that we are studying and trying to mitigate.
Yeah. The other one is from Lisbon. There is also a link with papers, and of course, it's just a message to cooperate, and for sure we will come back to you for cooperation. Another question from yeah.
Someone wants the mic, please ask. A question to APOLO. But it's a complicated question, so maybe it takes 2 seconds answer as well. So you showed 2 applications. One application that is power supply for auxiliaries from ammonia and ammonia cracking to fuel cells, and then another application that is ammonia combustion in engines, basically. So my question is, would you feel that there would be a business case that you could apply the ammonia cracking system for auxiliaries, even though ammonia would not be used as propulsion fuel? For example, let's consider you still have a fuel that is Cechetto based. Do you think that, say, end users, shipping owners, they would be able to implement this solution that means storing ammonia on site?
Yes. The use case we are taking for APOLO is an ammonia ship, ammonia carrying ship. So we already be having ammonia on board, and it won't be a passenger cruise for sure. So we were targeting in an ammonia ship which already has it, so that we would have an unlimited supply of ammonia to crack. And yes, in this case, I think H2 site has already demonstrated that you could use this ammonia cracking system for a short-term for auxiliaries. So the use case we are doing, we have a ship company, a standard in our group, who is providing us with the technical specification of an ammonia membership. And from there, we would be checking like, okay, auxiliary, like there are partners like Corvus, which we have in our group. They already have a fuel cell, propulsion using fuel cell and ship propulsion. Like it's a short-term navigation, but still. So they are very interested in, taking it to the next level and maybe propulsion one day. But yes, of course, if it's ammonia and if you're using engines, for example, then we need to talk about the NOx emissions. And we are in APOLO, we are also working on NOx decomposition catalysts, N2O basically. So this is how we are trying to tackle this. Even though it's not the framework of our project, we are thinking about because Cechetto site is very keen on doing it and taking it to the next level. If that answers your question.
Thank you very much. Yes.
First of all, I have one confusion regarding the plasma combustion. There were two terminology used. One is ammonia cracking and one was ammonia combustion by plasma system. So I just want to get clarification which one is the part of this project, or are you working on both? And the second question, and that one is about what was the reason to use nanosecond pulse for ammonia? You mentioned that you are using nanopulse. And especially when we say that we are using renewable energy, it is most of time it comes as a DC energy or with low frequency. So changing energy also costs some energy.
Thank you. So yeah, the cracking, I think that's a misunderstanding of terms. We are with plasmas, we are cracking ammonia in-house with dissociating ammonia. This is part of the process that will lead to the combustion of ammonia. What we aim is combustion of ammonia, right?
Yeah, but at this moment you are doing combustion with plasma, supplying air, right?
Yes, of course. Yeah.
Not correctly.
Yeah. But some cracking will happen anyhow by electron impact dissociation. The second question was about, sorry, forgot. Why nanoseconds? So in literature, in what we call plasma assisted combustion, it's a pretty, let's say, old field. There are studies with different kind of plasma sources, from DC, from lighting arcs, from AC, DVDs, microwaves, etc., etc. And then there's a huge community that deals with the nanosecond pulse discharges. And these kind of discharges have some very, very unique attributes, which are, first of all, that they can trigger kinetic mechanisms that are unique compared to the other kind of sources. Secondly, that they can trigger thermal effects, which are very, very important also for the combustion process. So what we call these ultra-fast gas heating mechanisms. And thirdly, they can also induce what we call hydrodynamic perturbations in terms of shock waves, which are very, very important also for combustion purposes. So our focus was to focus on these kind of discharges because we think that all the benefits that they give, in the end, they can, let's say, help and they can overcome any potential penalties, let's say, from energy conversion, etc., because indeed you need some pulsars that can provide from DC to some nanosecond pulse. And these are unique pulsars that in the future you can see how we can maybe miniaturize them or commercialize them or reduce the energy penalty that is attributed to them. But this is something down the road.
Last question. Okay. So regarding this pulse, most of time when we talk about the energy efficiency, there are two different methods to measure the power. So one is the plug-in power and the second one is with the pulse power, because we know that with the pulse power, actual energy spent is very low. But if we compare energy efficiency with that very short pulse, we will see that very less energy use.
But the density is very high.
Yeah,
yes.
Yeah. So, but the energy waste during making this pulse can be only be checked by the plug-in power. So how you are measuring this power? Plug-in or the just oscilloscope?
Until now, we're not, because we are again in the beginning of the project. Down the road, though, believe me, we'll have partners that they are experts in nanosecond pulsed plasma technology, and they know exactly how we can measure the power, which can come directly from oscilloscope measurements, from specific oscilloscope measurements, because now we're talking about nanosecond pulses. So this can give you exactly the power that's consumed by the discharge, and then of course you can measure very easily also the power that comes from the grid, right? And then it's consumed, which is not going to be the same for sure, because the generator will have some consumption and so on.
Yeah, but I think as a suggestion, I also agree, we should report both.
Yeah, maybe, yeah.
So I have a question for Valentina, because your project is not about ammonia, as you said. Which part of the project can contribute to ammonia energy, and for which project, for example?
Thank you. Perhaps if we look just at we work with membranes, so I would focus on that part. If we consider, for example, the carbon membranes that we use for gas separation, in the end, that's a little bit what they are doing, for example, in AndreaH project. Carbon membranes can be used also, for example, for hydrogen separation. And in the end, it's just let me use this term, matter of fine-tuning the membranes, basically how you fabricate them. And then in the end, you can easily, so in this case, in brackets, separate the gas that you want. So for example, if you look at the cracking of ammonia, you could have ammonia cracking and you could use membranes for hydrogen separation, or as they do also in the AMBHER project, you could use carbon membranes for ammonia separation during synthesis. And of course, they are opposite processes, and it would require, of course, the fine-tuning of the properties of the membrane. So it's not an easy task, but in principle, it's possible.
Thank you very much. There are other questions online.
Cooperation.
Sure, of course, we will cooperate. Other questions? You have a question? Yeah. No, that's also good. You said not to me.
No, it's for you, actually. So I have a question for you.
It's for me.
No, it's not.
That's okay.
In literature, it is often reported that when you combust ammonia, it is easier if you use a blend with hydrogen. And I think that's also what's the plan in APOLO project. It is about flame stability, basically combustion, and as well as emissions. Would it be the case that if you use plasma, you also solve partially or for this issue, or is it at least reduce? Because I think that you are targeting just burning pure ammonia, but does using plasma allow also basically to have inside process basically hydrogen production or not?
Thank you so much. It's a very, very to the point question. And it's true that, of course, hydrogen blends with ammonia seem to stabilize flame and enhance characteristics of ammonia combustion. What we aim to do in our project is to have a pure ammonia air mix. And then to be on the safe side, we already said that we might need to have in the starter phase a little bit of hydrogen. Our goal is to have zero hydrogen injection. And we know by the literature and from different studies that we've done, partners in the consortium, that plasma indeed helps a lot. And it can reduce significantly the amount of ammonia needed to stabilize the flames. So we'll see down the road how this goes. Yeah. Can I make a very, very quick comment? Because you said in the beginning also the question about the energy efficiency. We are having right now, as we talk, some very, very nice collaboration in Cabinet project between two partners, and they're running some very unique experiments on ammonia dissociation and to study the energy efficiency of non-pulsed plasmas in ammonia decomposition. This is something that hasn't been done yet, so it will be very, very interesting. We'll report on that as soon as we have these results.
Yeah, very good. So I have another question that is for all of you, because you many times also during the other presentation was said that ammonia is a dangerous chemical. Which project does the safety also study? So, want to say?
Yes, well, anyway, we are now in the preliminary steps with the safety analysis of the project, but this is included also, is carried out by Rina is in charge of it, but we still don't have a start or we have just started.
For APOLO project, we have a health and safety analysis because obviously we want this technology to be in the maritime applications. So it's very crucial that we study it, and we are also like we have an ammonia producer company in our group, Faria, who has a lot of experience in ammonia safety generally. So we have their expertise. And we also have a team from Technaria who would also study the health and safety issues. It hasn't started yet because APOLO is in its starting the third year. So now it's where we start. And so I can't say much about the results, but also we are looking for the IMO regulations. So these kind of studies will be done for this project.
Safety is an integral part of our project too. We haven't done it yet, but we have to do it. I think Green also is a partner of the.
Well, there is cross-fertilization.
Yes, exactly.
Right. So first of all, of course, the experimental work already in our facilities, in our university has to include this. So obviously in the project, safety has to come first, and then for the implementation is part of the de-risking assessment. So we have the people at LCE, one of our partners in Italy. They are going to look at these potential risks that you could run, how to mitigate, and what are then safety or environmental regulations we have to keep an eye on. Especially if you think of decentralized manufacturing of chemicals, that's a very big part of it.
Yeah. You want to say something?
No.
You don't have ammonia, so that's good.
Okay, I think there are a couple of questions. First one, across your projects, what do you see as the single most important milestone for green ammonia to achieve real early market adoption? Lower costs, certification, downstream technology readiness, or port and logistic availability?
People working with ammonia.
Okay.
I see Valentina is going to
Right. I have to be honest with you. I see this from the perspective of technical development, and from my end, there are a couple of challenges that we see ahead of us. One is the stability of the catalysts during operation. I think for many of the industrial partners, maybe in the audience as well, they know traces of oxygen can deactivate severely iron-based catalysts, but also ruthenium-based catalysts. They tend to vary to have substantial orders of magnitude lower activity if you have water or oxygen. So for us, it's a big part of our project is developing catalysts that can operate in the presence of these traces without having to have a sacrificial bed, for example. So for us, that's one priority, technically speaking, and then the same also applies for these ramping up and down of operational load. So how would you deal with thermal stresses that might arise from changes in the reactor operation temperatures and so on? So we see these as the main challenges from the point of view of technical aspects, and it's maybe down the road where we will look at all these more system level kinds of regulatory and policy type of barriers.
Mm-hmm. Others to comment?
Very quickly for me, because our project doesn't deal with cities with ammonia, but using green ammonia in the end. So hopefully we have green ammonia and its cost is not that high and everything else is sold. Again, as Jimmy said, in the technological perspective, well, we need to move on and to try to make the combustion of ammonia efficient, safe, and with environmental emissions that they are under regulations and under permissions of worldwide, the European Union. And this might be the driving factor that will lead to the adoption of this technology in the future.
I'll talk about APOLO because that's where we really study about the ammonia, and we have an ammonia producer, as I said. So for me, industrially speaking, I would say the cost, because that's what our ammonia producer was always keen about, because green ammonia costs a lot. The electrolyzers are not fully developed for a green ammonia synthesis. So I think that would be a key driver for the for making ammonia a bit for a front runner for this technologies.
Yes, I agree that the cost is very important. For if we understand ammonia like a hydrogen carrier, companies or industries that wants to invest on it must understand that it's cheaper to have this ammonia and use the hydrogen from ammonia than using electrolyzers to produce the hydrogen. For example, in the case of AndreaH, it has been studied, the AndreaH case, in which ammonia is produced in the Iberian Peninsula, where we have more renewable resources to produce the hydrogen. After that, produce the ammonia and transport the ammonia to the end user, which is in Germany. And the other case is the direct production of hydrogen in Germany and use of the hydrogen or to inject it in the pipeline directly in Germany. And it has been carried out a preliminary cost benefit analysis. And in a preliminary stage, it was clear that the cost is lower if you produce this hydrogen in another regions and you import it, is what Luna was commenting in the morning. Yes, so I think the cost is important and the acceptance of ammonia as the provider of hydrogen.
Yeah, indeed. I think also in all the comments that you find against ammonia, you should be fair about the comparison that you do, right? Something else that I till now I saw perhaps only in the presentation of H2 side, but an argument against hydrogen and ammonia is always that in principle you can use batteries, right? Do you compare your technologies with not other fuels, but perhaps with batteries? Did you do, perhaps while writing the project, did you do this? I see Jimmy, perhaps.
Yeah, so we did quite a bit of studies on this, and I'll show, kind of the motivation is actually seasonal energy storage. And for that, you really cannot rely on batteries.
Yeah.
Is that very short?
Very clear, actually.
So intermittency during the day, if you have peaks or so, or day-night operation, you can deal with batteries. But if you have the summer, winter periods, then you have to have a system, chemical storage. And also scalability at the terawatt scales, which is what we need for some of these, then you have to go with chemicals.
Want to learn? There is another question online.
Yes.
Perhaps you can read.
For aviation industry, and I'm really curious about the applicability of ammonia and its role in future aviation fuel, especially in the face of the current geopolitical instability.
So aviation fuel.
I come from the aviation, not industry, but research, also aerospace engineer by education. So in our Caipirinha project, we're very lucky to have also a partner on AndreaH from France, which is the French Aerospace Lab. So we are very much wanting to study how the aviation industry in general might be interested in ammonia as a fuel. And we're also very lucky to have in our advisory board Airbus. I would say, from my perspective, from what I know until now, they're not looking to ammonia seriously as an alternative fuel. They're going full force for hydrogen and for electrification, of course, aviation. But in all these industries, they're open to new findings. So I hope that all the projects that we try to push ammonia further will open up their eyes to these industries, and maybe in the future could be a very, very promising alternative for the aviation sector, which is quite challenging on its own because the engines themselves are quite different than the ones that we've been talking today. So it needs a lot of work to be done in the future, but it's all about showing that the results are interesting and that there is potential for this industry. So that they can uptake this technology.
Thank you. By the way, a follow-up of my previous question, because I saw that many projects look at safety. I guess these deliverables will be public. Yeah, so that's very good. Yeah. Question. Yeah.
I have a question regarding AMBHER project about the LCA that the last presentation we had. And in that one, it was mentioned that you are still working on total to find the how much greenhouse gas involved per metric ton of ammonia. So what is the scope of that project? Will you make the comparison with different technology? And do you have something in your mind as a benchmark, how much CO2 emission will be involved per metric ton for ammonia? And the second part of this question is that LCA scope is only greenhouse gas emission or also toxicity or other land use or water management is also part of this LCA?
I think very quick to answer this question.
It's not here.
I'm sorry, I can't.
That's I can say. So the LCA, of course, will not look only at the CO2 greenhouse gas emission. We'll look at a variety of other indicators. And for us, the benchmark is the AMBHER. So we try to compare to that. Considering that the AMBHER is commercial and the arena will stop at TRL 5. So it's a very small prototype, so we have to do the projection.
And sorry, is there any estimation of the emission per ton metric ton?
Yeah, in that case, indeed, the lady should be here because I don't have.
Yeah, I have one question for Apollo and one for Leisure. For Apollo, actually, I want to ask that what is your expectation of energy generation after your fuel cell system? I mean, actually, you expect that you can actually supply all the energy demand of, for example, your offshore system, like, I don't know, ships or something like that, cruise ships or bigger one, or whatever actually moving on the, offshore from the fuel cell you have on the board or not?
So what we are thinking right now is fuel cells for the auxiliaries and the engine for the propulsion. But we are thinking about like in the framework of the project, we are thinking 125 kilowatt power. I know it's not great for a long distance shipping, but the partners are very keen on scaling it up and exploiting this whole thing. So we are targeting around 30 megawatt of power generation from this technology, but it has a slightly longer way to go, I would say.
Yeah, perhaps just to add, there's a balance between what the call what the call was asking, what that was TRL 5, and what the company want to achieve, that is going faster to commercialization. So indeed, is a very small fuel cell, is 125 kilowatts. But of course, there is already the study for 2 megawatt and 10 megawatt. And you had another question?
Yeah.
Yes.
Sorry, I want to know if you actually the gas separation membrane you're working on, you think actually you can use it even for ammonia cracking downstreams or not? If they are polymeric or ceramic question.
So as I mentioned before, for gas separation, we use carbon molecular sieve membranes. So they are carbon-based. There's a aluminum support, and then the selective layer is a carbon layer. And then it all depends on what are the separation mechanisms that you use basically to separate the molecules that you want to separate. And then in this case, because they are carbon molecular sieve membrane, basically what you use is molecular seeding. So you separate based on the size of the molecule. So you could indeed use this type of membranes also to separate ammonia or hydrogen if you go for cracking. But then it is about tuning the pore size of your selective layer. So basically, in this case, if you have ammonia and you do ammonia cracking, so you produce hydrogen and nitrogen, you need to have a pore size distribution, which is able to discriminate what goes through and what stays in the retentate site. So what is left behind. So you should be able to have a membrane that lets hydrogen go through, but leave behind the nitrogen in this case.
Yeah, this membrane is actually the one Camille
Yes,
explained before. So do you have any smaller prototypes that
yes,
you're working on as a replacement for?
yes. Maybe,
Yeah.
yeah. What?
So just to implement what Valentina was saying, the membranes developed in measured indeed would discriminate between hydrogen and nitrogen. So you can put directly after the cracker, also the temperature is not a problem. You cannot put inside the cracker because they are not selected for ammonia. And yes, there is a prototype of 1.2 square meter of membrane being assembled now, and then will be tested for the separation of hydrogen. There is a question online. Oh, it's open. There is a question to stop. Okay, very good. Then thank you very much for the introduction to the project. And